Okay, so here we go with the end of the first chapter of Calc 2. We're basically going to be putting together all of the different techniques for integration that we know. At the end of the day, you're not going to be told which one that you need to use, so you need to be able to choose pretty carefully. In some cases, it's going to be pretty obvious. When you see a rational function, partial fractions. When you see powers of trig functions, it's a trig integral, but sometimes it's not. I will be making a couple videos of some pretty standard ones, and then maybe one or two videos of some real tricky ones. So here we go. I want you to pause the video and try these first. Okay, I'm assuming you have. Let's go through them one by one. So for the first one, I notice I have a polynomial here that I can probably factor. I'm going to take out an x, because I notice they have those in common. Then I can factor that x squared minus 4. Okay, so now I'll go ahead with my partial fractions. I have a over x, b over x minus 2, c over x plus 2, and that's 1 over that. Multiply everything by that denominator. And I get a times x squared minus 4, because the x's cancel out and I'm left with these two, plus b times x plus 2, c times x minus 2, and that's 1. So I'll FOIL everything out. bx squared plus 2bx, cx squared minus 2cx, and that's 1. And then I'll just equate all of my coefficients. A plus b plus c, a plus b plus c. I have that many x squareds over here. How many do I have on the right hand side? I have 0. 2b minus 2c. I have that many x's on the left. How many do I have on the right? 0. Negative 4a, that's my constant term on the left. On the right, it's 1. So here we go. A is real easy to find. Then A is, I won't use white for this because I have my problems in white. So let me change that color. There we go. So I got A is minus a quarter. I'll plug in minus a quarter here, and then I'll actually, so I have minus a quarter, so I'll add it over on the right hand side, and then I'll multiply everything by 4. Hopefully you can see the algebra going on there. 4b plus 4c is 1, because I added it over so the negative sign went away. Hopefully you can see that. 2b minus 2c is 0. So I guess to solve this system, I'll multiply the second one by 2. So I'll get, instead of this, I'll get 4b minus 4c. Then I'll subtract them. There's a couple ways to solve the system. There's 4c minus minus 4c is positive 8c, is 1 minus 0, so c is 1/8. And then if I go here, this equation, the second one, gives me 2b is equal to 2c, so then b is equal to c. So I have c is the same thing. It's a 1/8. Now, just so I'm not going to scroll off this page, I'm just going to erase all of the partial fractions. Oh shoot. I have to leave them here but erase everything else. Because I know what A, B, and C are. I have minus a quarter, 1/8, and 1/8. So instead I have to do that integral. And now I can just do those separately. It's negative a quarter ln x plus 1/8 ln x minus 2. And then I've got an eighth ln x plus 2. My plus c, and that's it. Then we'll go ahead and do the second one. E to the x tangent e to the x. So this one, first off, jumps out as a u sub to me, because I have e to the x, and its derivative e to the x is being multiplied all on the outside. So I'll do that u sub first. U is e to the x, du is e to the x dx, so that I get the integral of tangent of u, and then these go away to make du. Tangent of u was one of the previous videos that became a table integral after you know how to do it. It's going to be ln of secant u plus c, which is ln of secant of e to the x plus c. And that's it. So number 3. X minus cosine x all squared. Well, from here, actually, I think probably foiling out is the best way to go. If you notice after you FOIL this out, these all become integrals that you know. The first one is just a real easy x to the third over 3. The second one is integration by parts. And then the third one is one of the trig integrals. So let me do this separately. This integral becomes, I'll do the integration by parts. 2x is the easier thing to differentiate, so I'll do that. Du is 2, and v is sine x. So I get 2x sine x uv minus integral v du. Integral of sine is negative cosine. Negative cosine cancels the negative sign here. And that's it. So I can just replace that. This integral I will do in another color. Remember your half angle. 1/2 1 plus cosine 2x. That's 1/2 x plus 1/4 sine 2x. The 1/4 is because of the half, and then I got to bring another 2 out. And then it's plus here because the antiderivative of cosine is sine. So now I can put all the pieces together. The first part, x cubed over 3. I subtract off this entire thing. So I gotta distribute that negative sign. And then I gotta add this on. Plus c, and that's it. Moving on. X plus arcsine x over square root 1 minus x squared. So what do I see? Well, I see I have arcsine and its derivative here, but I actually don't think I want to go for a u sub just yet, because this x is probably going to get in the way of that. So for now, I'll leave it. I do notice, though, that the two integrals, if I split the fraction, become doable. This one is just a u sub, and this one looks like, well, actually another u sub. This u sub becomes 1 minus x squared, negative 2x dx, throw in the negative 2, and get rid of it. So I'm going to write it separately. This integral is negative a half integral u to the minus a half du, which is minus a half times add 1 to the power and divide by the new power. Divide by a half turns into times 2, which is minus u to the half, which is minus square root 1 minus x squared. Okay, in another color, I'll go ahead and get this one done. Write it in a different blue. I notice I have arc sine x and its derivative 1 over 1 minus x squared square root is being multiplied, so that's what I'll let u equal. du is 1 over root 1 minus x squared dx, and I have the integral. Here's u, and what I'm circling now is du. It's dx times 1 over this. So I just have u du, which is 1/2 u squared, which is 1/2 arc sine x squared plus c. And so what do I have to do? I just have to add these. So the original integral, x plus arc sine x over root 1 minus x squared, is negative square root 1 minus x squared plus 1/2 arc sine x squared plus c. And that's it. Two more. Wish there was an easier way to do this, but there probably is. I could probably lasso it, but what are you going to do? Number 5. So I've got the integral of secant to the 4th x dx. So this is one of my trig integrals, so I have to figure out, do I want to let u equal secant or u equal tangent? I have to figure that out kind of in advance. I think that u equals secant is a bad idea. If I took u equals secant, I would have to take out a secant x tangent x. And I can change secants into tangents, but they kind of come in twos. Every secant squared turns into a tangent squared. It's really hard for me to just take out one. So you can try it if you want. It's probably a good exercise to see why that doesn't work exactly, but just my gut feeling tells me that tangent's going to be the way to go. So du is going to be secant squared. So that means I got to pull out a secant x squared dx to become du. How many am I left with? Well, I've got 2 left. Fortunately, having 2 secants is enough to bring out a tangent. Secant squared is tangent squared plus 1. Now I can actually do the u sub. This becomes integral u squared plus 1. Secant squared x dx becomes du. u3 over 3 plus u plus c. And then u is tangent x. Perfect. So moving on to the last one. Let's see if I can just lasso this. Oh. Perfect. I'll just do that from now on. So the sixth one, x arctan of 2x. So this definitely looks like an integration by parts problem. So I got to pick my u and dv. I think usually you let u be a linear term, but I think letting u and dv go this way is a problem, because then I have to do the integral of arctan, and nobody likes doing that. That's another integration by parts problem. So we'll avoid doing that. We'll let u be arctan of 2x and dv be x. So v is x squared over 2. du is, I got to be careful for my chain rule. Inside is 2x. Arctan something is 1 over 1 plus that something squared. Then multiply by 2. So I've got 2 over 1 plus 4x squared. Now I'll do my integration by parts. X squared over 2, arctan of 2x, minus the integral v du. X squared over 2, the 2 and the 2 is going to cancel, so I'll get x squared over 1 plus 4x squared. And if you remember from partial fractions, whenever we get an integral like this, you gotta do long division. So I'll do the long division over here. I've got x squared and 4x squared plus 1. How many times does 4x squared go into x squared? Well, it goes in a quarter. I'll add in my placeholders. So now I gotta subtract minus x squared minus 1/4. Then I get minus 1/4 over here. So I'm left with 1/4 minus, whenever I get a number over here, I leave that denominator. So I've got, just recopy my answer, x squared over 2 arctan of 2x minus the integral of 1/4 minus 1/4 times 1 over 4x squared plus 1 dx. Okay, now we got x squared over 2 arctan of 2x minus integral of 1/4 is x over 4. Then I have the integral of this part. Looks like an arctan, but I have to just be a little careful about it. I have 1 over 1 plus 2x squared. So I'm going to do a quick u equals 2x. du is 2 dx. So I get minus 1/4, throw in a 2 dx, then divide by 2. So I've got minus 1/8 integral 1 over 1 plus u squared du. X squared over 2 arctan of 2x minus x over 4 minus 1/8 arctan of u, which is 2x, and plus c. And that's the final answer. So I'm going to be making a timestamp for this. Moral of the story. There's 2 things I want you to know about this at the very end. The first part is that you have to be able to know which method to use before you know how to do the method. It is harder to know what method to do sometimes than even how to do the method. I think integration by parts, for example, is easier than just knowing when to use it. The second thing I want you to know is that there is more than one way to do a problem. If you did a problem different than the way I did it, that does not mean you're wrong. In particular, for example, with this one at the end here, there are a couple different ways to do that end up being exactly the same. But your work does not have to exactly match mine, so I don't want you to worry about it. So, in fact, with many integrals, there are more than one ways, just total different methods to do it from the get-go. In the next video or two, I'm going to give you a couple examples of those. But for now, we'll just leave it here. And I hope this was helpful.